Okay, next we talk about some of the terminology related to probability models, and we start with experiment. Rather than defining experiment, let me define random experiment, because I mean, writing this prefix random from prefix random makes much more sense when we talk about experiments. Experiment is any procedure that you do that have more than one outcomes, maybe several outcomes. So, for example, you might end up flipping a coin, and the outcome or the result of the experiment. So you flip a coin, the outcome that's an experiment. You flip a coin. Now the outcome of that experiment might be a head, or it might be a tail. So that's what the experiment is just flipping a coin, and the outcome might be head, might be tail. We do not know whether it will be head or a tail, but it can be one of the several outcomes. So that's an experiment. On the other hand, if you roll a die, for example, that's an experiment. You roll a die, that's an experiment. And the outcomes now are, maybe it comes up 1, it maybe comes up 2, 3, 4, 5, and 6, where we are assuming that the die has 6 faces. You may have another complicated kind of experiment, in which you have a coin in your hand. In one hand you have a coin, and in the other hand you have a 6-faced die, and you simultaneously toss a coin as well as roll a die. That's experiment. And now the outcomes might be, the coin may end up as head, and the die may come up with 1. That might be one outcome. Another outcome might be head with 2. Another outcome might be a head with 3, so on, a head with 6. Each of these is one outcome of the experiment, or all these with the tails. In this particular case, we have 12 possible outcomes for this experiment, and one of these outcomes is going to happen as a result of the experiment. We call the experiment random because we do not know which outcome will appear. It is completely random. Even though if the coin is biased, and it is constructed in a way that the appearance of head is more likely than the tail, even if there are chances of the tail to appear, even if a very small chances of a tail or head is there, we will still call the experiment at random, because even though there are high chances of head due to the construction of the coin, the randomness of appearing as a head or tail is still there. So the experiment is called random, because whatever outcome the experiment will result, that outcome is random. We do not know what that outcome will be. And obviously the goal of probability theory is to predict those kind of outcomes. What are the chances that this outcome will appear? What are the chances that this outcome will appear, and so on? That we will see later in this video. But it should be clear that an experiment, normally random experiment, is some procedure that you do that may have several possible outcomes, and which outcome is going to appear as a result of this experiment is random. Which means if you repeat the experiment, maybe another outcome appear. If you repeat the experiment again, maybe another outcome appear, and so on. So that's why you do not know which outcome can appear, and so the experiment is called random. Third, we talk about sample space. Basically, the set of all outcomes of an experiment. If you just write the set of all the outcomes of an experiment, that is called a sample space. So sample space is simply you list all the outcomes in a set, and that is called a sample space. So this is, for example, sample space of experiment 1. This is sample space of experiment 2, and this is sample space of experiment 3. So set of all possible outcomes where no single outcome is left out, and there is no element in this set that is not going to occur. all the possible outcomes then that can appear, all possibilities. You just list them in a set, and that is called a sample space. Third, we talk about event. Fourth, we talk about event. Event is any subset of sample space. When we talk about subset, we may end up confusing the event with an empty subset, because empty subset is also a subset. Events normally are non-empty subsets. So you have a sample space, and an event might be any subset of that. Consider, for example, you roll a die, that's your random experiment. The sample space for that, let me denote the sample space as S, or in our case, that is basically the universe. So let's denote that as omega. That's all the possible outcomes for a 6-face die. Yeah. So you roll a die, that's the, and one event might be, you might be interested in, or you might win the game if an even number occurs, any even number. So this might be an event. If 2 occurs, if the outcome 2 appears, then you may win the game. If 4 appears, you may win the game. If 6 appears, you may win the game. So basically, for winning, you are interested in this particular event to occur. We say an event occurs if any of its outcome appears. So if you actually roll a die and a 2 appears, then we say E occurs, the event occurs. The event occurs even if a 4 appears. And if you repeat the experiment, for example, and a 6 appears, we say event occurs. So occurrence of event means any of its outcome basically appears as a result of random experiment. Now we move towards probability model from event to basically a number. Consider, for example, consider again, your coin is fair. That's your assumption. Your coin is fair. And the experiment is you toss a coin. So the sample space basically is heads and tails. That's the sample space. Now what's the probability? Maybe you're interested in an event. You are interested in an event that a head appears. That's one event. Let me call that event as E1. Maybe another event is a tail appears. In this case, we have these 2 kind of events. Let's say events of interest. Now the probability of event 1 is just a number, that actually signifies the confidence of E1 to occur. If the coin is fair, for example, if there are 50-50 chances of heads and tails, then the chances or the predictions that a head will appear or this event will occur, that is 0.5. Because later we will see the probability numbers, they range from 0 to 1. 0 means no chances, 1 means 100% chances or certain, and inside it is the relative scale of probability. Similarly, the probability of E2 is 0.5 in this case. But it might be possible that the coin is constructed in a way that the probability of head or event 1 might be 70%. The construction company of that coin just reveals that the coin is biased and the head is 70% as likely as the tail. In that case, the probabilities will be that. And but what these probabilities will be, you have to rely on that. Or if you have a toss, if you have a coin, then toss that coin several times and see, for example, toss that coin 1,000,000 times and see what fraction comes up as a head and what fraction comes up as a tail. And that will give you a reasonable estimate of the likelihoods of what is going to happen next in future. But finding out these probabilities from data, if you toss that coin several times and you come up with these kind of rules of probabilities, that's a task of statistics. But once the rules are available, then you are doing prediction on the upcoming events. That's a task of probability, as I mentioned earlier. Further, we can have, for example, let's say we have roll a die and 1, 2, 3, 4, 5, 6. And let's say we have an event of even numbers. So 2 appears, 4 appears, 6 appears. So we are interested in, for example, what's the probability that an even number appears? Well, that's a probability that the 2 appears, or so probability that event 2 probability that event occurs with 2, that probability. So let me write that as 2. Then the probability that a 4 occurs, then the probability that a 6 occurs. So you add up all these probabilities, and that's the probability of event. So if event has more and more outcomes, it is more likely to occur because one of its outcome becomes more probable to appear as an outcome of the experiment. Next, we talk about some axioms of probability. Actually, first axiom and the foremost axiom is the probability of any event must be non-negative. That's the first, or that's one axiom. That's one rule. The probability you assign to any event must be non-negative. Another axiom is, or the other rule is, the probability of two events, E1 union E2, if you have two events. Remember, this E1 is a set, E2 is a set, E1 union E2 is eventually a set. That is basically probability of E1 plus probability of E2 if E1 and E2, they are disjoint. If they are disjoint, then the probability of E1 and E2, union E2, is simply the probability of the addition of probability of both events. If they're not disjoint, I mean, the more general formula of this is like this. They may be disjoint, or they may not be disjoint. In that case, you have probability of E1 plus probability of E2 minus probability of the intersection, because the intersection is counted twice. Remember, the intersection elements, they appear in E1 as well as in E2. So towards the chances computation, they are counted twice. So we have to subtract one of its contributions to balance out the overcounting that we did. And in that case, the probability of an empty event, or the event that is 0. With this assumption that the probability of phi, or empty event, is 0, this formula is consistent with the formula of disjoint events. And this is also true for more than two events. If you have several events, if all events are mutually exclusive or disjoint, then the probability of the union is just the sum of all the probabilities. The third rule is the normalization rule. The probability of the sample space itself is an event, but that event is certain. Remember, the sample space, one of the outcome of the sample space is going to happen. So what's the probability that sample space occurs? Sample space is also a set, that's an event. If that set is treated as an event, that is for sure to occur, because one of the outcomes of the experiment is going to appear, and every outcome is in the sample space. So this is for sure true. So, I mean, first of all, the probability assigning to every event is is non-negative. For mutually exclusive events, the probability of union is just the sum of individual probabilities. And even if they are not mutually exclusive, even if they are not disjoint, you just account for the overcounting you did, and the probability of sample space, which is the sure event, that is 1. So that way the probability of any event stays between 0 and 1. So yeah, I mean, these axioms should be kind of rules must be taken care of. There are several rules that you can now, for example, derive. For example, if A is a subset of B, then probability of A is smaller or equal to probability of B. That is the direct consequences of these rules. And there are several other rules. For example, For example, let me write probability of A union B is always smaller than or equal to probability of A, probability of B, where A and B are events. And this becomes equality if A and B, they are disjoint. Otherwise, this will stay smaller and this will stay larger. Yeah, so, and there are several conclusions that you can make on different kind of relationships among different kind of events. Remember, each event is a set. Next, we talk about conditional probability. For example, what do we mean by conditional probability? Well, if you, for example, let me explain the conditional probability with an example. Let's say you roll a die, for example, and your sample space is this: 1, 2, 3, 4, 5, 6. Let's say that's your sample space. Assume event EI is simply I, where I varies from 1 to 6. So that's event I. And further assume all the events, all the outcomes, they are equally likely, which means this is 1 over 6. So the chances that 1 appears is 1 over 6, the chances that 2 appears is 1 over 6, the chances that 3 appears is 1 over 6, and so on. So now let's say you have an event. Let's say you have an event E event. Let's say this event, which is 2, 4, and 6, all the even elements. Let's say this is event E. Now the probability that E2 occurs, E2, remember here E2 simply means that the outcome is 2. That probability is 1 over 6. But imagine if you are going to do the experiment, if you're going to roll a die, and before rolling a die, somehow you have a belief that this event will occur. That is somehow belief. Your belief is that this event must occur. Somehow you have this information that this particular event will occur for sure, or this event is certain, for example. In that case, how will you utilize that information in estimating this probability? Well, without that information, the probability of the event E2 is 1 over 6. But with this information available, the probability of E2, given the information that this particular event must occur, now the probability of E2 changes in a way that because this event is going to occur for sure, your sample space changes. And now your sample space becomes this. Because if this is a certain event, this is going to happen, then all the outcomes in this particular event, one of them, they are going to appear for sure. So now this becomes your sample space. And in this particular sample space, what is the probability that a 2 will appear? Well, all the probabilities, they are equally likely for normalization, if you normalize that. So the probability of this 2 occurring is 1 over 3. The probability of this 4 occurring is 1 over 3. The probability of this 6 occurring is 1 over 3. So in that case, the probability will become 1 over 3 rather than 1 over 6 because you have utilized this particular information. So conditional probability is probability of an event conditioned on the information of some other event. So for example, if some event is going to happen for sure, and you have that information, then the probability of events, they may change after utilizing that information inside the model, and all that stuff is known as conditional probability. And by the way, conditional probability is just another probability law after you have utilized your condition inside. So using the condition will change the sample space. Once the sample space changes, all the probability of different events, they are renormalized so that they add up to 1, and the probabilities, they will get changed. So the formula, for example, is the probability of A given that B must occur, what is the chances that A will occur? Given that we know that B must occur or B will occur for sure, that is the probability that both A and B will occur. The chances that A and B will occur, both of them, divided by the probability of B. So you now can think that this probability of B, this normalization factor, that is like the sample space normalization, B is acting as a sample space, and A intersection B is acting as an event from this particular sample space. We are not getting anything that is outside B. So that's what the conditional probability, in a very crude sense, in terms of events, what conditional probability is. Next, we talk about the total probability theorem. That is very, very powerful theorem that uses this conditional probability. So for example, what's the probability of, let's say, A? A is some event. The probability of A is the probability of A and B1 plus probability of A and B2 plus probability of A and B3. I will shortly tell you what do we mean by B1, B2, and B3 and all that stuff. Assume B1, B2, and B3, they are disjoint events and they form a partition of sample space. So assume B1, B2, B3, they are a partition, they form a partition of sample space. Then probability of A, how can you calculate the probability of A? The probability of A then is probability of A intersection B1. So what's the probability of A? The probability of A is the probability of, what is the probability that A will appear? Well, A can appear as along with B1, or A can appear along with B2, or A can appear along with B3. That's it. That's a probability. And that is known as the total probability theorem. In the last slide, as I have mentioned, you could have seen this formula. Let me rewrite that formula again. And here, this probability of A intersection B can be written as probability of A given B into probability of B, just by the formula that we saw in the last slide. If we just pull this B over here, we get A intersection B to that. And with that, this particular total probability theorem becomes probability of A given B1 into B probability of B1 plus probability of A given B2 into probability of B2 and probability of A given B3 into probability of B3. And these partition sets need not to be just only 3. They can be 2, they can be 3, 4, 5, 7, or maybe countably infinite. They may be infinite of those, but they should be countable. So yeah, so that's the total probability theorem, and very, very useful in a lot of cases. One very powerful use of this conditional probability is also there in Bayes' rule. So Bayes' rule is the following. So consider, for example, you know that in sets A union B is the same as A intersection B is the same as B intersection A. That's no doubt. That means so A intersection B and B intersection A, that's the same set. So now the probability of A intersection B must be equal to the probability of B intersection A. But by conditional probability law, we know that probability of A intersection B is probability of A given B into probability of B, which is equal to probability of B given A into probability of A. And here we can just see probability of B is probability of A given B is from the left to right. It is probability of B given A into probability of A and divided by probability of B. That is called the Bayes' rule, and it is used extensively and heavily in inference. Almost all the classifiers, all the machine learning stands on this rule. And that rule comes very naturally through the conditional probability. So probability of A given B is simply probability of B given A into probability of B and divided by into probability of A divided by probability of B. I will show you the examples of Bayes classifier and inference. Actually, we will implement that in Python in the next video series as well. I mean, this is the first part of the video series. In the next part of the video series, we are going to implement all these concepts that we are seeing here in Python as well. But it should be noticed that this simple rule, I mean, very natural and simple rule that can be derived very easily with a few steps, all the machine learning, all the classification, all the regression theory stands on this. All the estimation, that estimation is whether the maximum likelihood estimate, the parametric estimation, or the maximum a posteriori distribution map estimators, even Bayesian estimators, they all stand on shoulders of this Bayes rule. And there are direct ways of estimating this left-hand side without actually countering the ingredients, and that is called, sometimes called in machine learning, that is called discriminative learning. And there are, and if you learn this left-hand side using the individual components, for example, this component and that component and that component, you learn all these three first and then you arrange them in this way and you actually got the formula for this. That is called the generative learning. Both have their benefits, merits and demerits in machine learning, but any machine learning model is either generative or discriminative. One way or the other, you are calculating this left-hand side. Let me give you an idea. For example, what's the probability that a face image that appears right now, the face image that appears right now has identity, let's say 5. It's a image of the fifth person where the image is just appears right now, that image. What is this probability? By Bayes' theorem, we can see that the probability of this is into probability of y equals 5 and divided by probability of x is image. Although I'm talking here in numbers, in variables, not as events, we will see later on we can convert the events to variables called random variables. But just to show you that all the, I mean, classification and regression theory, they use these kind of formulae to build face recognition systems, to build object recognition systems, to build speech recognition systems and all that stuff. I mean, each and everything is there. You build this, you predict this left-hand side through Bayes rule. Yeah, that's very powerful. One last concept in probability models is this independence. Independence is if, for example, you try to compute, for example, probability of an event A given the information of event B, and the B is no longer informative, or A and B, they are independent completely. The occurrence of A does not depend upon the information that B supplied. In that case, the probability of A will stay as it is, whether you know the occurrence of B or not. For example, let's say A is event that you roll a die, let's say, and A is an event that an odd number appears, 1, 3, and maybe 5. That's an event A, that an odd number appears. So the probability of A is 1/2 if we assume the equally likely faces, all the faces are equally likely. The probability of A, so let me write that here, probability of A, that is 1/2. But what if I say that what is the probability of A given the information that is not useful, or about an event that has nothing to do with A? the probability of A will not change in that case. Although if we know that event must occur and stuff like so, in that case we say A and B, both the events, they are independent. So if the information if A and B are independent, then knowing the occurrence of B does not affect the probabilities on A, and that means the events A and B, they are independent. And a direct consequence of independence is that probability of A and B can be written as probability of A and probability of B, rather than writing, because if we write it in this way, then if they are independent, then these two are equivalent. So that's what independence means. In several cases, when we read real kind of data, there are several features in the data, and some features are independent from the other features. And when we build probabilistic models on those kind of features in a joint way, we will see the joint distributions later on. It is basically possible to exploit that independence information to build more concise, more efficient, and more valuable probabilistic models as compared to otherwise. Conditional independence is another concept. Sometimes, for example, maybe it is possible that the event A and B, they are not independent, which means A intersection B is not equal to A and B. It is, let's say A and B, they are not independent, but it may be possible that given an information about some other event, maybe some other event has occurred. Now it may be possible that the two events, they become independent given this information about the third event. And in that case, we say A and B, although they are not independent, but they are independent conditionally, conditioned on this event. And this is possible. Maybe A and B, they depend heavily on each other, but once another event, the information about another event is available, given that information, A and B, they may not depend on each other heavily anymore. So yeah, so that's about the very basic theory of probabilistic models in terms of events and sets and all that kind of stuff. I moved very basically from set to these kind of models and probability laws and axioms and all that stuff. In the next video, we will be moving from events to variables called the random variables. And these are the random variables that are much more important, because when we read real data from different files to build probabilistic models on that, these real data, the attributes of that data, they actually are variables and called random variables that eventually represent certain events inside. But working with the variables, working with the numeric data in terms of variables will give us much more statistical analysis as compared to events. For example, we can compute the averages, we can compute the expected values, variances, spread of the data, and spread of a particular variable, random variable that represents an events, for example. So representing events in terms of variables, random variables, to come up with a numeric form will give us a very powerful tool to work with real data, and to analyze the real data. So in the next video, in the next video series, we will start from random variables. We will convert events to variables to numeric form. And there we will actually be playing with all the real kind of data using all the concepts that you have seen here in this particular video. We will extend these concepts to variables and then to real data, and we will actually build very beautiful models, probabilistic models and statistical models on real data. So if you like this content, please subscribe our channel and like this video and share to your friends and press the notification button so that whenever our new video or new notifications they come, you get notified immediately. So hope to see you in the next video series.